and today we are going to talk about distributed loads and what it is, how are we going to use it, how do we find the information that we want, how we're going to represent it and all of that. So let's get started. Okay, so what are we learning in this session? So first thing we're going to talk about is what is a distributed load and why should we care? Okay, so that's item one. How do we describe them? So what is a mathematical way of describing distributed forces? And what's a systematic way to compute the net force and net moment due to distributed force? Well, why do I care about net force and net moment? Remember, when I have to do equilibrium, I have to find out net force, net moment, okay? And then, how do you use a shortcut for commonly occurring cases? You know, if you do a systematic complete version, sometimes the calculations will get kind of long because you have to do some integration and so on. But for common cases, there's a shortcut that you can do which will help you a lot. Okay, so let's get started. So first question, what is a distributed load? If you looked at our problems up to now, we have always had loads which were concentrated. What I mean by that is, we had loads which were focused on only one point, and basically we knew the total force, say 600 pounds, and where it was applied. Okay, and the units for that was pounds or Newton. That's what we did, right? This is a typical example. But in many situations, that's not happens. For example, wind loads on a building or wind loads on something. So for example, if you look here, if you are near the ocean, you will not get a single point load. What you will get is a load spread over a huge area. Okay, the load at any particular point will be very small, negligible actually, but it will add up. So think about it this way, wind is not, even if it's a hurricane, the force of the wind is not that high compared to say a bullet or something like that, right? But because it acts over a wide area, it can have devastating effect. So we have to be prepared for that. And in fact, this is the same thing if you're doing an oil rig, for example. Underwater, the forces due to the water current will be very, very large, and you have to account for it. And it's not acting at just one point. It's distributed all over the place. That's why we care about it. Skyscrapers, for example, are built with distributed loads. If you are interested, you should look at what happened to the City Core building in New York City. So go type City Core distributed load on Google, and you will learn a lot about how important wind loads were for that building and how close to actually completely collapsing it came. So go take a look at it. It's a very fascinating study. Okay, very good. So we now know that distributed load means load at any point is very, very small, but it is spread over a huge area, and the unit for a distributed load is usually what you call pressure. So when you hear about water pressure or something like that, we're talking about a distributed load. But pressure is only one kind of distributed load. There could be others. And the unit in 3 dimensions for this will be Newton per meter squared, or PSI, pounds per square inch. And in 2 dimensions, it will be Newton per meter, or pounds per foot, or pounds per inch. So notice the difference in the units between this and that. Okay, very good. So now let's talk about how are we going to represent it. So if you have a concentrated load, what you do is you can represent it pretty simply. You can represent it as force at particular locations. So in this particular case, you have a 400 pound force at 0, and then 800 pound force at 3 feet, and then 800 pound force at 6 feet, like that, right? So it tells you where the force is and how much it is. You can actually write it if you are used to what is called the Dirac delta notation, and if you are used to a Dirac, technically what's called a Dirac delta distribution, you can rewrite it. So delta x minus x naught means 1 unit at x naught. That's the meaning of this Dirac delta. So now you have 400 units at x minus 0, which is written as delta x, 800 units at x minus 3, which is x equal to 3 is when the force is, and then 800 units at x equal to 6. I'm just this is not that important at this stage, but I'm just showing you that even concentrated loads, you can write it in some kind of a notation. What do you do with the distributed load? Now look at this one. Notice that the load is distributed over the whole beam. It's like a sinusoidal distribution. And if you look at the load at any particular instant, this is not the load, it's the load intensity. How hard am I pushing at that point? It's a load intensity. Okay, and it's given by as a function W of x, and its unit will be Newton per meter. So in this particular case, W of x looks like sine pi x over 2L. This is the counterpart to this kind of thing. And since it's distributed, every value of x is allowed. Here only distinct values of x are allowed. You see what I mean? There every value of x is allowed. That's how distributed loads are described. Very good. So now, when you're interested in figuring out what are the forces at the joints because of this distributed load, suppose I want to find out what's the effect here or what's the effect here, I need to find out how much force am I applying and how much moment I'm applying. So how do I do this? Now calculus to the rescue. Okay, so this is where we are going to use our calculus skills. So first item, here's some distributed load. You can see that it is distributed according to something. Wx is the load intensity. Df is the incremental load in this region, which is equal to W of x dx. That's how much load is acting per small region, and the smaller the region, the smaller the force. But what happens is the net force will add up. It's a sum of all of this. So first item is the net force is the sum of all the elemental forces. So which is integral from A to B. So if this is A, if this is A and that's B, then it is the integral from A to B of that, which is this net area. So if you want to find the net force, you have to find the net area under the graph. And net area under the graph, is an integral, right? So the net force due to a distributed force is equal to the area under the graph. The net moment looks like some x minus xp times, if I want to find the moment, let's say at this point xp. Then I do x minus xp times df, which is x minus xp times wx dx. So this is the incremental force, this is the moment due to that force, and it's the first moment of the distribution. Now you're thinking, okay, I got to do some integrals and all of this stuff. Yes, welcome to why we learn integral and differential calculus. So here is a chance for you to look at integrals. It turns out this is equal to the net force times the distance to the centroid of the force distribution. So if you want to figure out where the centroid is, then it will be equal to the net force times the centroid. How far is this? So what we are going to do is we are going to take a distributed force like that and replace it with an equivalent concentrated load F total acting at the centroid. So where it acts, the equivalent load where it acts is called the line of action. This line of action, and you obtain that by calculating the centroid. And you're wondering, hey, you know what? This looks familiar, right? This is what we did for gravity. So when we looked at gravity, if I look at a lump and I looked at the force of gravity, gravity is pulling for every point in the body. So it's a distributed load. We replaced it with a single load at the centroid of the body. That's exactly what we can do to any distributed load. All distributed loads are like gravity. You have to find the centroid and stick it up there. Okay, that's how it works. Got it? Very good. Now let's try first example. Here's a very simple one. I got a big like a frame on which some bricks are sitting. Each brick dimension is given, and it turns out that it corresponds to a distributed load of 300 Newton per meter over a length of 1.4 meters. This point is A, this point is B. Here is my x component, here is my y coordinate, and our question is, what is the force on this? So how do I do that? First step, this is our systematic approach. This will always work. Step 1, write the force function. In our case, that looks like W of x equals, it's a constant function, no? You can see it's constant and its value is 300. So it is 340 Newton per meter. Hey, that was easy. In other cases, in this particular case, it's not a function of x. So that's very nice. So now we want to find out F total equals integral. A starts out at 0, B is at 1.4 of W of x dx, which is integral 340 dx from 0 to 1.4, which turns out to be 476 newtons, which is equal to the area under this graph. 340 times 1.4. Very good. How about the moment? Integral, I'm going to calculate moment around A. So it's x minus 0 W of x dx. This is x of A, which is, I'm doing this in a kind of a painful way, but you know what I'm doing, right? Integral 0 to 1.4 of 340, that's W of x, x times 340 dx, which turns out to be equal to 340 times 1.4 whole squared over 2, which turns out to be, how much is that? 1666 over 5 Newton meters. You could have done this in a different way. You could have said this is equal to a single force of magnitude equal to the area 340 times 1.4 acting at a distance of 1.4 over 2, you know, the centroid of a rectangle, right? 1.4 over 2, and so you can calculate moment equals 340 times 1.4, which is the force, times 1.4 divided by 2, which turns out to be 1666 over 5 Newton meters.